Hello students and welcome back. Hopefully the test went well. We're done with Unit 1, but we are going to move on to Unit 3. If you want to follow along in the book, I'm looking at page 162 at this picture by one of my favorite artists, M.C. Escher. Now M.C. Escher, maybe not a household name, but I bet you've seen some of his pictures in your math class. He has the one about relativity where there's a bunch of people walking upstairs in all different directions. And M.C. Escher wasn't necessarily a mathematician, but he did great things with art and mathematics. The one we're going to use right off the bat throughout this problem, or throughout this lesson, is this one with its lizards. And I made a little transparency, and as you can see, Escher used a framework first. He actually made these triangles first, and then he tiled the plane. Hopefully you remember that from Math 1, tiling the plane where we have a shape that can kind of interlock with all of these and have no empty space. He tiled the plane with these lizards. But this unit is about similarity and congruence of triangles, or just similarity of shapes. So we have a shape of a lizard. Now if you look, it's pretty close to that each one of these lizards fits within one of the triangles. Maybe a little bit higher here. But the lizard in triangle 1 isn't actually similar to triangle 5. Now they're different colors, I know that, but they're both hooking to their right. This one's a little bit bigger than this one, but then look at the one from 1 and 2. Well, this one's hooking to the right, this one's hooking to the left, but this one's bigger than 2. I wonder if they're actually similar shapes. So one of our goals in this lesson is to know what it takes to actually be similar figures, and then the characteristics, how we can use those similar characteristics to find different lengths or missing pieces. For example, here's an old picture of an iPhone, and then we have a quarter in the bottom right. And again, this is in your book on page 164, it looks like. So you can try it in there, or you can try it on the screen. And what I want you to do is read number 2, and says that when a camera lens is positioned perpendicular to the plane containing an object, the object and its recorded images are similar. So if I know shapes are similar, I can actually use the information from the picture to find some actual dimensions. So what I want you to do is try and find the dimensions of the iPhone. Or it could be an iTouch, don't really know for sure. Now I have some markings over here, which is kind of maybe a little hint, but I actually give you the diameter of a US quarter is 2.426 centimeters. So if you notice, one of these little lines, that looks to be like the diameter. So maybe I can fit how many diameters actually go into the width of this iTouch or iPhone, whatever it is. It looks to be about 2 1/4. Quarter, get it. And then we have 1, 2, 3, 4, about 4 3/4 with its height. So tomorrow in your notes, what you're going to bring into class, I want you to see if you can tell me the actual dimensions of this iPhone. Now in real life, the US quarter is 2.426. Not necessarily in this picture, but they're saying that they're similar. And we'll talk tomorrow about the assumptions that we're making with this, that we can actually use this type of picture. So come with those dimensions, see if you can use the similarity of that. So let's think about what it takes to ensure that triangles are similar. Let's just focus on triangles. Well, in this picture, I need to know that the real life image is similar to the picture. And they say we assume that. When that's the case with triangles, I need to know all corresponding angles are congruent. And yes, we need to know all 3 sets. So the angles in the same spot have to be exactly the same. The second condition we need is all corresponding sides aren't congruent, but are what we call proportional. Now you may have heard this before. They have a common scale factor. And that's what we're going to talk about a lot in this lesson also. And it has to be corresponding sides. You always have to match short to short, medium to medium, and long to long. That's very important. We're going to try and trick you and rotate these Always match short to short, medium to medium, and long to long. So let's look back at Escher. Okay, Escher's framework says that he uses isosceles right triangles. Isosceles right triangles mean two sides are congruent, and we have a right angle. Now, in problem number 4 on page 166, he says assume BC is 2 units long. 2 units from here to here. We'll just go 2 units. What I want you to do for tomorrow's homework, and I'll give you some hints, is show that triangle 1 is similar to, and there's the similar symbol, to triangle 2. Now we have to have these conditions. We have to show all the angles are congruent and all corresponding sides are proportional. So I'm going to help you, especially with the angles. So usually when I want to show this, I'll go angles and I'll go sides. Angles. How big is angle C in this triangle ABC? Well, if it's isosceles, I have this as 90. Each of these angles have to be the same. They're base angles, so each of these is 45 degrees. Now let's look at triangle 2. It's still isosceles. I have the 90. This is 45. This is 45. So it checks out. The 45, 45, and the 90 in the other triangle does go to a 45, 45, and a 90. So all the angles match up, so let's start looking at the sides proportions. Well, what I have to do is actually find some side lengths, which I can do if this is 2 units. Because if I do AC squared plus AB squared, that's going to equal 2 squared. But what do I know about AC and AB? Oh, they're the same length. So I can actually write this as AC squared plus AC squared equals 4. Now the little step right here, if I was writing this as a proof, this would be a substitution. Now I have 2AC squared equals 4. AC squared equals 2. So AC, the length of AC, is the square root of 2. Normally take the square root plus or minus, but it's geometry. That length is square root of 2. So it's that one. So it's square root of 2, square root of 2, 2. Now, let's look at how the lengths work out in this triangle C to the midpoint down to here. I know it's the midpoint because I have 2 little double slashes. That means this little length is 1 unit. This little length is 1 unit. So now we start setting up the proportions. This leg would technically be a short leg in the big triangle. Okay? So I would say square root 2 is 2. Now I got to look at the short leg of this one. Well, let's say it is to this one. Square root 2 is to 1. As, let's go to the other leg. Square root 2 is to another short leg. Maybe medium leg in isosceles, it's kind of nice. Square root of 2 is to 1. But now let's match up the hypotenuses. 2 is to, well, how long is this? Well, luckily, notice that this is a square, so we actually know it's square root of 2. So are these 2 triangles similar? Well, they would have to have the same scale factor. Are these 3 things equal? Take a minute and see if you can see if they're equal or not. Hopefully you see, obviously these 2 are, but look at this blue one, 2 root 2. We don't leave it as 2 root 2. 2 root 2 is the same as this. We have to rationalize it. So it's multiplying by 1. I'm not changing the value. So it would be 2 root 2 over 2. Look at that. We have a common factor of 2. Square root 2 over 1. So these sides are actually in proportion. Triangle 1 is similar to triangle 2 because I showed all 3 angles, corresponding angles congruent, and all 3 corresponding sides have a common scale factor between those. And that's, at this point, that's all we're going with. We have to find all 6 things. So Escher, in his awesome wisdom, said that this one's similar to this one's similar to this one's similar to this, and he used the square root 2 factor, or 1 over square root 2 factor, all the way down, all the way infinitely down to these really tiny triangles, and he kept drawing those lizards based on that, based on similar triangles. So then he ensured that the lizards were actually similar. Okay, moving on. So now we're going to see how we can use this similarity on problem number 5 on page 166. And it's going to be a bigger portion of your homework, so it's very important. For 5a, Monisha conjectured that all isosceles right triangles are similar. And we want to prove to see if that's true. So if there's any that you can prove, I'd like you to prove them as best you can. And then if there's some that you don't think are true, just show a counterexample, one way that it doesn't work. So again, Monisha conjectured that all isosceles right triangles are similar. So we got to show, just like we did, all the angles and all the sides. 3 sets of angles are congruent and 3 sets of corresponding sides are proportional. So to keep it general, let's say this side's A and this side's A. It's an isosceles right triangle. Well, if that's the case, then this would be K times A, and this would be K times A, where K is some scale factor. That if I'm going from small to big, I'd multiply by something, and then I'd get a longer length thing. But since it's isosceles, it would be Ka and Ka. Now let's think about what this third side would be. Its actual length would be square root 2a. And we saw that on the Escher one, but it's good to know 45, 45, 90-degree triangles, AA square root 2a. Now let's actually see. Think about what we would want this to be if it was similar. If this is truly going to be similar all the time for any a value, this should be k times c, or square root 2 k times c. And I don't really know if it is. Or square root 2ka. My apologies. It's going to be square root 2 times as big as this side. So let's actually prove this. Now if I was to set up the Pythagorean theorem, I'd get ka in parentheses squared plus ka parentheses squared equals, we'll just call this length x. I don't know what it is yet. I'm going to have some expression for it. Now ka squared, please do not say that that's ka squared. It's k squared a squared. Make sure ka times itself is k squared a squared plus k squared a squared equals just x. But let's look at this. How many of these do we have? Well, we have 2 of them. Let's combine them. 2k squared a squareds still equals my x. My x squared. Well, if I just want this x length, to find out what it is, I actually have to take the square root. You notice I kind of caught myself there because I kind of wanted to know where I was looking, but that should be x squared. If I take the square root of this, we should be able to simplify this. This becomes the square root of 2. The square root of k squared is k. The square root of a squared is a. Equals just x. So look at that. It is the square root of 2a times the same k value that we had for the other sides. So, with that work aside, maybe we'll keep that in your notes. All the angles, 45s, 45s, 90s. Now the sides are a goes to ka, or a is to ka. Let's write it correctly here. A is to ka, as a is to ka, as our last side is square root 2a. Well, that is 2k times square root 2a. Ran out of room there a little bit, but as you can see, there's just this common k factor with all 3 of those sides. Okay, so what I want you to do is B through E. I'll make a conjecture that all equilateral triangles are similar. So then you're going to have 3 sides that have this common scale factor. Does that mean all the angles are congruent? Okay. Maureen claimed that all squares are similar. Now we're getting out of triangles. Got to show all the angles are congruent, corresponding angles are congruent, all the sides have a common scale factor. And again, if not, write a counterexample. So the last thing is when we know 2 triangles are similar, we have what's called a similarity statement. So naming these triangles is very important. The order in which you name them is very important. I have a triangle ABC here. That does not mean it's similar to DEF. We don't always just go in alphabetical order. So I might have to fill some information in, maybe using law of sines, cosines, Pythagorean theorem to find some stuff. But then I match my 3 angles, my 3 sides. If you can see here, that angle is going to be 60 using the triangle sum theorem. This one's going to be 80. And that helps me match up what I'm matching up angle-wise. So I have my 40 angles-wise. I got 40s matching up. I got 80s matching up. I got 60s matching up. They all match up. Angles are set. But how about the sides? Now, here's the very, very important part also. Match short to short, medium to medium, long to long. So the short side on this one is 4. Red side. What's the short side on the big one? DF. 4 is the 10. Now let's go medium. 9 is to the medium on this one is 22.5. Which, then lastly, the long side of this one, 12 is to 30. And you can try it with your calculator, or just look at reducing these. 4 is the 10. You got the 2/5. 12 is the 30. That's also 2/5. We can take a 6 out of there. The 9 out of 22.5 is a little bit different, but if you check it, it actually does work. And this should be a green side, I just noticed. So all 3 sides do check out. These are similar. So the similarity statement, how we're going to start this is going to name the triangles. If I name this triangle A, B, C, I want to say it's similar to triangle. And then I look to see what I did. On ABC, I went short, medium, long. So over here, I have to go short, medium, long, or I went red, blue, green. So I go short, medium, long. D, F, E. That's our similarity statement so far. Eventually, we'll have a theorem of why we can say it is, but right now, just naming those triangles. Because this says A is a corresponding angle with D. C is a corresponding angle with E. And guess what? We can do that with the sides also. Side BC matches with FE. You can check BC match with FE in my triangle. We want to know which sides match up, and we want to know which angles match up. So lastly, in your homework, bringing in for tomorrow, I want you to try this problem. Here's all your given information. I say angle A is congruent to X. B is equal to 100 and Y is equal to 100. I give you length of AB is 10, BC is 20, CA is 25. XY is 37.5, YZ is 15, ZX is 30. I want to know if those triangles are similar and write a similarity statement. Tell me which triangles are similar. So hopefully this is a good start to similarity of triangles. Again, at this point, we're finding everything. 3 angles, 3 sides. Make sure you have that scale factor. Have a great night or evening. Have fun, and I will see you tomorrow.